Okay, still on this impulse and momentum on the rigid body, kinetics of rigid body. Here we look into the eccentric impact, okay, where we have a 10-pound slender rod, okay, and it is suspended from point A up here. If there is a ball B here, and the weight of the ball is 2 pounds, and it is thrown at this particular rod and strike at the center with a velocity of 30 feet per second. And for this particular problem, we want to determine the angular velocity of the rod just after impact. Okay. Okay. After the impact, this particular rod for sure will swing. Okay. Here we assume that it will swing to the right. Okay, making a counterclockwise motion. The coefficient of restitution, or sometimes we also refer as the how to measure how elastic is the during the impact, and here it is given as 0.4. And to begin with, we look into the angular momentum of the system before and after. Okay, what happened before? Okay, before the impact, we can see that the ball is moving at the speed of 30 feet per second. So there will only one item that is moving, right? So rod is at rest. So on the left hand side, we only have VB. So VR or V rod 1 is 0. So we only have this part here. Okay. So actually we have MR VR1 times 1.5 because the G is here, right? So however, this particular part is 0. Okay, so we only have this part. And on the right hand side, what we have is after the impact, or we can look down here. After the impact, the ball will not stick to the rod. Okay, because we know that the coefficient restitution is equal to 0.4. Okay, it is not equal to 0. If it is equal to 0, it means that the ball is stick together with the rod. Okay, because the value of coefficient of restitution is between 0 to 1. If the value is equal to 1, it is considered as perfectly elastic. And in this case, it is 0.4. So it is considered still with elastic problem. Okay. So now we assume that the ball is moving to the right hand side. So it is a positive. This is our reference axis. The right is our positive. So we assume that the ball is going to the right, okay, after the impact. And then what we have here is the motion, okay, of this particular rod at the speed of Vg, okay, the speed at the center here, Vg, or here, this is our Vg2, okay, this one, Vg2, okay, Vg2. Then the distance is also 1.5. And then the last part here is the rotation that will occur due to this impact. Okay? So Ig omega 2. Okay, after you plug in all the values, okay, and you know that the Vg2 supposed to be equal to, because Vg2 here, see Vg2 is on this particular rod, so Vg2 is equal to RGA times omega 2. Okay, so RGA is 1.5, so 1.5 omega 2 Vg2, and not for the ball. Okay, because the ball will not stick to this particular rod. So you cannot say that the ball is equal to 1.5 omega 2. No, will not be like that. Okay, only for the rod in this case, because the ball here will bounce back. Okay, now after you resolve this, you will end up with this particular equation. So we have equation 1 right now. Okay, equation 1. And on this particular equation 1, we have two unknowns, which is V ball after impact and also the angular velocity of the rod, because the rod will swing. Okay, now since we know that the value of this coefficient of restitution 0.4, so now we can use that particular value to get another set of equation. Okay, coefficient of restitution is nothing, it is the relative velocity, okay, after impact or collision. I put it impact here, okay, or collision, or relative velocity before impact. Okay, so what we have after impact. Okay, after impact, we can see that the rod, okay, Vg is representing the center of mass of this particular rod, Vg2, okay, after 2. So you can see this both is with subscript 2. So the rod minus the ball, okay, and then down here, the before impact, what you can see is the ball minus the rod. Then you just plug in the value, and the for this particular rod, we know that is given Vg2 is here, okay, is given here 1.5 V omega squared, omega 2 minus VB2 divide by, we know that VB1 is given here 30, or this one, VB1, 30 second. And then we know that the rod is initially at rest, so it is 0. So now you rearrange this particular equation here, you will get another set of equation. So we have now two equation and also two unknowns, and therefore we can easily solve for this particular problem to get the value of VB2 and also the omega, or the angular velocity of the rod just after impact, okay, which is 3.65 radian per second. And for this for the ball after impact, we can see the value is negative, which means that the ball will bounce back, and the ball is moving to this direction, okay, with a velocity of 6.52 feet per second. Thank you.